Swayam Prabha. Digital India. Educated India.
So good morning. We're still hoping for a few more. Your classmates will show up in the next few minutes, but we will get started. So today we're going to do more sort of general introduction, but it's going to be about life cycle thinking and life cycle assessment. And so we're going to do a combination of some lecture and then some activity. So including in this room this morning, we'll do some hands-on work, a little longer time than what you had yesterday for the hands-on work, then a little more lecture. And then this afternoon, we are going to be in a different location and we will do some more hands-on getting you started. And at that point, we're going to be getting you started on your project, which will be sort of, you'll do a little bit along the way until next week, Friday. So we'll sort of repeat what we did this morning, sort of in general, but you're going to get to think about your project even starting this afternoon. And that's a way for you to really think things through. And internet research, real quick, is always very valuable in all of this stuff because we don't all ever know everything there is to know about any process. So you always have to go and learn about a process because you cannot do a life cycle assessment without thoroughly understanding the system that you are studying and the environmental impacts that they cause. All right, so this morning, I just really want to think about life cycle thinking. And as I introduced yesterday, sort of the circular economy is the outcome that we want, right? That the materials and energy flows are moving between systems and not just getting disposed of, right? Not this linear account. The life cycle assessment is one tool that we have to evaluate, are we making it, where are the problems? What should we fix to make it less environmentally impactful? And how do we go about knowing that if our changes are better than we started? Remember yesterday we talked about some unintended consequences that happen when you don't do sort of life cycle thinking. Even if you don't do the whole assessment, still just thinking about this can help you prevent those unintended consequences. So now this is the tool that we're going to start talking about that we will be using to some extent. In the brevity of this short course, you can't really do it all, but we'll give you enough information so that you can move forward with that. So our objective is to give you the ways of thinking and a starting point to actually go do it yourself. And it sounded like some of you are already there trying to do it yourself. All right, so when you talk about life cycle, to some people like an entrepreneur or an innovator, do we have any entrepreneurs or innovators here? You also often think about this kind of a product life cycle. So you got to be really careful when we talk to other people about what the life cycle is. And this is in terms of developing a product, manufacturing it, selling it, and then sooner or later it might be obsolete. Just think about those, what are the little toys that maybe kids have, right? Like a couple of years ago, we had these little spinner things. Did you have those here? Right? Are those still around? No, right? So that is a very short product life cycle, right? Somebody came up with this idea, it caught on, everybody wanted one, everybody bought one, boom, no more sales. That's an example of a product life cycle. But that's not what we're talking about here. We're talking about the life cycle that comes with the circular economy from the extraction of raw materials and resources from the earth all the way through its life, hopefully with a lot of reuse and recycle and recovery in the middle, but there's always going to be some ultimate end of life. So this is what the life cycle that we're talking about here. So just make sure that when you're talking to other people, they understand that there are those different ways of talking about life cycles. So everything from raw materials extraction, manufacturing, operation use, and waste management or something at the end of the life. I just want to start with some vocabulary words. So we've got some things. So these things in yellow boxes or even the sub boxes, right? Manufacturing would have a lot of boxes, right? There's a lot of steps that make up that one big box. These are called the life cycle stages. And often we want to understand the environmental impact by the life cycle stage, because then that can tell us, oh, we need to go fix this part or that part. We need to figure out what is causing the biggest environmental impact so we can set our priorities so that whatever changes or improvements we make are really meaningful. We also have the system boundary down in the lower left here. The system boundary is sort of the box around which you're doing your life cycle. And sometimes we have different system boundaries. You might have a system boundary that looks something like that, and we would call this a cradle to gate. It's just the manufacturing process, and all of the early things are sometimes called the upstream. Right? You might know how you're manufacturing something, but you have no idea how the steel that you're using in your product was manufactured. That's those upstream processes that we have to figure out how to incorporate them into our life cycle thinking as well. Even though we might not know anything, we don't have access to the data, we still have to do that. And sometimes we also have what we call the downstream processes, are like the end of life after it's gone through this use and reuse cycle. So we've got upstream, downstream, could be cradle to grave, but anyhow, there's some sort of a system boundary around it that you would decide based on whatever your goals are. So just back to the vocabulary here. Well, let's see. So what we need to know is we need to know how to make a product, what it's made out of, how those materials are made, how we use it, how long we use it, what do we do with it when we're done using it. If you really truly want to do a life cycle assessment, you need to figure out all those things. And often there's a lot of really big assumptions made with all of those aspects. So I'm just going to start with some really simple examples here. So a ceramic coffee cup, right? So you all know, right? We had our chai in them yesterday. Ceramic coffee cup. We're going to go through all of these steps: raw materials, manufacture, use, disposal. So what do we know about it? We know it's made from ceramic, right? We know there's some sort of glaze on that. If you don't know, most glazes are made from minerals. Different colors come from different minerals. So you've got some abiotic resources there associated with the metal. And of course, you would need water and energy to do that. The manufacturing, often sort of, if it's not a handmade pottery, ceramic, it was pressure molded and then baked at a high temperature kiln. So we've got the equipment associated with that. We've got the high temperature kiln, and then it's going to be packaged. So you've got all the materials that you need for the packaging. And then use, you know how to use a coffee cup, fill it, use it, wash it, repeat, right? And finally, disposal. There's not much you can do with a ceramic coffee cup. You could upcycle it, do some artwork with it, but generally, if it falls and breaks, is the end of life, and then it typically goes into a landfill. So those are some of the material aspects of what goes into a coffee cup. We also have transportation steps every step of the way. And so that one broken coffee cup might take a tiny corner of the transport for each step. But yes, there's some energy and emissions associated with that. So if we're going to draw a schematic now, this is what we're going to spend a lot of today thinking about, is like, how do you incorporate all these processes into sort of what we're doing? So we've got these are the things that we just talked about, right? Not the transportation, but everything else. But make the cup. but really there's a lot of many steps here. So in reality, that might be lots and lots of boxes, right? How many of you have drawn process schematics in some class, engineering class, chemical engineers, process flow diagrams? Nobody? Yes? Yes, somebody? Just how materials flow through a system, right? It might just be that how to make a cup, but you've got all sorts of systems, unit operations, you got to connect them dots. Okay, so to make the cup, we needed that clay mineral extraction processes, right? Again, there's probably a lot of little boxes in that big box. We know we need water, and we know that the water gets used for, it goes all directions, right? So the water goes all different ways. In all steps, we use water. All right, so that's a really basic. So now let's sort of build this out some. So we said there's going to be some packaging on the cup, which means that same cup needed some aspect of, we'll assume it's cardboard. You have to make the cardboard, so you need the whole forestry and manufacturing process. We need energy, right? We need electricity to make the cup and to use the cup. We're going to wash it. You might have to, or if you're going to make your coffee to fill it. So we need electricity generation. I just used coal mining here as an example. Your electricity might be more complicated than just coming from coal mining. We'll talk about that tomorrow. And then we know when you use a cup, you used water to fill it and to wash it, but then you've got wastewater treatment as well. And then we can keep going and going and going. So we also know that there was a lot of transportation. So we need petroleum drilling and processing. That goes, it's got the arrows on, that's a transportation. So you've got a little truck there. That's a truck. So petroleum, natural gas that also can be used to make electricity. And this is still just a really simple schematic diagram. Some of the things when you make these, since a lot of you don't have much experience, we put the processes in boxes, right? There's mostly a verb in here on most of these. Extraction, treatment, manufacturing, make, generation, right? So there's some active processes happening in each of these boxes. What's not shown on here, in part just because there's not, then there's some material flow. So it's the materials flow between the processes, but the boxes are the processes. So this is still a simple schematic. What this doesn't show, and you might want to include, use a cup. So then we have coffee going into the cup, right? So you've got your make coffee. And then we've got water. Where was my water? Right? You've got water going into making coffee. You've got grounds going into the, so you ground the coffee, grow the coffee. Right? And so there's all sorts of extra steps there. But that's really part of using this cup. And so when we think about this, it's not just the material aspects, but if we're really going to think about a system and how we use these things and why we use the products that we use, we have to think about those things as well. And so things can get bigger and bigger. And obviously to grow coffee, you need lots of energy there too. You might need nutrients. So anytime you get to agricultural systems, they get bigger and bigger and bigger. And so this is the idea of figuring out everything there is to know about your system. Now, what happens if you don't know much about, okay, you've got a product, you don't know anything about it or how it's made or what materials it's made of? What do you do? If you don't know something. Yes? Right, you can't analyze it if you don't know. So how are you going to figure that out? What? I still can't hear you. Assume. We can make assumptions. Absolutely. Making assumptions is a critically important part. What's the basis of assumptions? You still have to learn something about it, right? What you do almost every day. Google it, right? Or whatever your, right? Your favorite way to just do some basic research. How do you make X? So it's a good way to get started. It's not going to give you all the details that you need. Sooner or later, especially if we want to quantify things, we might have to make assumptions. Like I didn't specify what color is this cup. You would use a different mineral if it was a different color, and therefore, I don't know. So I could assume something, right? White, maybe it's titanium. So I could make that assumption, or that there are all sorts of things. So yes, assumptions, and just, you've got all sorts of information tools at your disposal that make this much easier today, at least to understand the basic process and how does this work. Oh yes, don't ask ChatGPT to draw your diagram for you. It will come up wrong. And then if you don't know and you get ChatGPT, you have no way of saying that this is wrong. So do your due diligence and make sure that you know above and beyond what ChatGPT is going to tell you. I am not yet a fan. I know it's a useful tool. I know people use it a lot, but do not use it if you do not know enough to know if it's giving you accurate or very made up information. I've got a master's student who's going to just graduate in a couple of weeks. She had some reference in her master's thesis that she thought was correct, and we went to search it. ChatGPT had made it up and like totally did not exist. And she hadn't figured it out, but she was ashamed. But anyhow, all right. So where's the circular economy in using a cup, the ceramic cup? Repeat of yesterday's. Where's the circular economy? Okay, that's how it's leaving the cycle, right? It's going out of the cycle. What is the circle? Where do you find the circle? So that's, yes, it's leaving the circle. Where's the circle? You're close, but step before. So we could use it for some other purpose, right? Use it for a plant, right? So we could use it for some other purpose. Think upstream, earlier, before. So you're thinking end of life. Before the end of life, where is the circular economy in a coffee cup? Reuse it, absolutely. Thank you. It is a circular economy because it's something that we use and we use and we use. And of course, you have to use it a lot of time in order to make up, right? Every time you use it, you don't need to do this stuff. I guess you still need some water, right? But the rest of it is that you skip all of these steps. Every time you use that coffee cup again, right? But that's a lot of energy. And I'm gonna, Indu asked me to get a word in here. So there's embodied energy. And materials in all of those steps. So every time you reuse it, you skip all of that. Now, if you've got a styrofoam or some other hot, single-use cups, every time you use one of those, you got to do that whole upstream stuff. So that's, again, part of this, the value of the circular economy is we can skip all of that. But we have to reuse it enough, right? You don't want to just use it once and break it, and then you lost all of that material good. All right, so this is the basic idea. So what's the value of the circular economy? I just told you that. And so what's the value of the life cycle thinking in this, by thinking of this whole system? What's the value of doing that level of thinking? All right, so we want to see how it impacts the environment and how are we going to use that information? We can make the processes better. Absolutely. If we figure out that the biggest challenge here, and I'll tell you, we'll talk about this tomorrow, is making electricity out of coal, that's a really big problem. And so, but this might show us that a biggest chunk of the emissions come from using electricity, especially if we use electricity from coal. Or it might tell us that it's getting transported from China to the United States. There's a lot of shipping, transportation, and that's a big problem. Well, maybe you need to not make it so far from home. So by doing the life cycle thinking, you get to identify where those environmental impacts are and decide where you want to prioritize improvements. So that's the whole point of doing this type of work. All right, so we just talked about the general concept of a schematic, but I've added some more things to this diagram now, right? We just talked about raw materials and energy coming into our system, but we also have outputs. So we talked about the inputs. So what are the outputs of that system we just talked about? Outputs. Well, we talked about a broken coffee cup, right? That's an output. It might go to a landfill. What else is an output from this system? Just mentioned environmental impacts. So there's a key. Wastewater, absolutely. Wastewater that has to be treated.
Coffee waste.
Coffee waste, all right, absolutely. We didn't draw that in our diagram, but yeah, so you've got coffee grounds. You can put them in the landfill, you can put them in a compost system or an anaerobic digester. Okay, so coffee grounds. What else are the outputs from the system? Emissions from transportation, absolutely. Packing material, right? Are you going to landfill that or are you going to recycle it, depending upon what it is? Okay, so we've got to also account for all of these outputs as well as the inputs and the flow of materials between. All right, so if we look at our diagram again, all right, so we know we used energy, petroleum, and coal, natural gas throughout this system. So that's an input. But then we have water and wastewater, inputs and outputs. We have air emissions. Anytime, it's really easy. Anytime you have any combustion reaction, you know that there are air emissions. And you can identify what the primary air emissions might be. There are air emissions from other systems as well, but you know that there will be air emissions from all of this combustion. And we had a lot of natural resource extraction, right? Our ceramic, our mineral, water, all of that, coal, natural gas, all of that is extracting natural resources. So we might have some resource depletion as well. These are all the things that we're going to try to track in a life cycle assessment. Okay, so we have to understand the system before we can even start to think about numbers or any of those other things, or what all the detailed emissions are. And this is the basic, 4-box diagram, but we just showed in every one of those boxes, there might be several boxes. And even in the boxes that I just drew, we know that there are several more boxes. So we are going to think about how do we draw and understand the system. And remember, it's like I said, yes, everything is interconnected, right? So sometimes this gets really wild, especially with water and energy use and things of that sort. All right, so what are all the things that we might think about? Raw material extraction, both biotic and abiotic materials go into raw material acquisition, but there might also be a lot of not just the materials that you're extracting, but all the energy that it takes to do the extraction, or water that you need to do the extraction. Manufacturing, you've got equipment. Sometimes we include the equipment, the manufacturing equipment. That's part of a life cycle assessment as well. But there's also a lot of other energy and water and consumables and chemicals that often go into manufacturing. These are all the things that we need to account for. Operations, depending upon what it is, often there's some energy involved. There might be water involved. There might be waste every time you use it. So all of those need to get accounted for in your use. So you can imagine that these diagrams are getting bigger and bigger when every one of these boxes has all these other things in it. And final disposition is, landfill, composting or digestion. You've got to transport it there. You might have to pre-treat it. All of that goes into the recycling. So now we're starting to build all of these different options into our diagram of what a system is all about. Are there any questions on that? Because that's the life cycle thinking, right? Like, wow, all this stuff I need to know. I'm going to make some assumptions about some of it. I'm going to go read some pertinent, even if it's like a Wikipedia, 101 about how something is made. That's what you might need to get started, to know how to move forward. You might need to dive deeper than that, but it's a start if you don't know. So what we're trying to do here, now that we go from the life cycle thinking to the life cycle assessment, is to figure out how to transform all of that knowledge about the inputs and the outputs into an understanding of the environmental impacts. And we'll include in here social as well, though a lot of life cycle assessments really only get to, especially the quantitative ones, to the environmental impacts, which of course sometimes have social consequences as well. There are some approaches, some very simplified approaches to life cycle assessments, and we'll even do some of those, like a carbon footprint calculator. It's just going to tally up one impact, carbon emissions, but it often does that over a life cycle. So it's a life cycle assessment, but not lots of different environmental impacts. And then we also have the quantitative that are all of those things are accounted for. And this might be like a master's thesis work of projects, right? That's why we're not going to get it done here in 10 days. But if you really are doing a full quantitative life cycle assessment, there's a lot of work because there's a lot of modeling of systems. There's a lot of finding industrial scale data. There's a lot of making informed assumptions. And then doing all the math. So there's a lot of mathematical modeling of systems, which is a lot of what engineers do, is a fundamental skill set that you need for life cycle assessment. So quantitative and qualitative, but anyhow, that's what we want to do, is to figure out how we transform those inputs and outputs, processes into environmental impacts. All right. So I'm just going to introduce the steps of doing a quantitative assessment. Really, you could do this qualitatively or quantitatively, but engineers have a tendency to think more quantitatively. So some of you are chemical engineers, right? Chemical engineers? A few of you? Okay. Well, the first time I was learning about life cycle assessment, I had this, primer on life cycle assessment. And it read like, this is a chemical engineer's dream. And I really could relate to that because it's mass and energy flow analyses, right? Mass in, mass out modeling, mass and energy and reactions. But you can be a mechanical engineer, or environmental engineers do a lot of the same stuff also. But it's that kind of work is what it takes to really do a life cycle assessment. Okay, so components. The first thing we need to define our objective. What do we want to accomplish and why? What are we going to do? What do we want to come out of it? What do we want to know? Do we want to identify ways to improve an existing system? Do we want to compare two different products to see which one's better? So all sorts of different things that you can do, but you need to know what you are trying to do in order to design your system. We just talked about, we need to understand the process, right? And all of those inputs and outputs, we have to decide, does it make sense to do a cradle to gate just to the manufacturing process, or do you want to include the use and end of life as well? Then we got to do what we call the life cycle inventory. That's quantifying all those flows, impact assessment, transform those into the environmental impacts, and then finally the interpretation. That's when we decide what can we do differently, or how do we make some decision. This is a decision-making tool, right? We don't just do it to say, oh, done, I've got a number. We do it because we want to learn something about our system to make decisions to reduce environmental impacts. So I'm going to go through a couple of these. The impact assessment we're really going to talk about next week. But we'll get started on the other sections. And so today we're doing life cycle assessment, and then we've got a couple days to learn more about some of the components that would go into this, the energy systems, the water systems, the end of life systems, before we start to put all of that back together. So goal and scope, what's the product or service you're trying to address? And then we've got something called a functional unit, which is really the basis for comparison. How are we going to know, like, what is it that we're actually trying to compare? And then all the system boundaries, how we're going to do it, all of that goes into an LCA. So a functional unit is the basis for comparison. If our life cycle assessment is to compare two different things, sometimes those two different things are used quite differently. And actually, maybe I will go to this one first. So let's think back about that ceramic coffee cup, right? So if you want to compare the life cycle impacts of a ceramic coffee cup versus a polystyrene single-use hot water or coffee cup. Assume both hold about 0.3 liters, so it's about, I don't know, I can't do that in my head. I think in cups. Anyhow, about 0.3 liters. So it's, a moderately sized cup. Are we going to compare one polystyrene coffee cup to one ceramic coffee cup? Is that the best comparison? Exactly. So this one, because of this, it's getting reused a lot of times. The ceramic or the polystyrene cup just gets used once. So the function is to provide you with a capacity to drink coffee, right? That's its function. How are we going to make these comparable functions? Okay, so if we think about what's the life of a ceramic cup, any guesses? If you think about a ceramic cup at home, how many cups of coffee or tea you have a day, you multiply that out by, does that cup break every year, every 2 years? Do you have the same cup 5 years later? Any guesses? How are we going to, this is where you make the assumptions, right? How are we going to try to figure out how many uses, what might be a comparable use for a ceramic coffee cup? So it depends upon the user, absolutely. So there would be a range, but it's more about depends upon the cup. So even if it depends upon the user, they might drink fewer cups a day, but it might last longer, right? But yes, the user behavior is going to be very, very important in this. The quality of the mug might have an impact on, how long it lasts before it breaks. So, but we have to come up with some number, right? We know the functional unit is to provide some number of drinks. So I'll give you some examples. So I have a big tea mug at my office that I drink about 3 big cups of tea a day. So let's say I go to work 5 days a week. So that's 15 cups of tea a week, right? I have had that same cup, let's say 5 years, just to make the math easy, and go to work. Well, there's some vacation in there, holidays, so let's say, I don't know, 45 weeks. So let's say 50 weeks, just to make it easy. All right, so 50 weeks, 15 cups a week. 5 years, 5 years. Okay, can anyone do that math in their head? Say that again?
3,700.
3,750. Okay, I'm going to say 4,000, right? Close enough, right? I had all sorts of assumptions in there. 4,000 cups of tea. It hasn't broken yet, but so I might get 4,000. Now that's pretty high. Most cups are not assumed to get used that time. And this day and age, you get so many coffee cups or reusable disposables. They're only good if you use them a lot of time. So what's going to be, how am I going to compare that one ceramic cup to a polystyrene cup? 4,000 polystyrene cups, right? EPS, expanded polystyrene cups, right? That's what you would have to compare, not 1 cup to 1 cup. So we've got this idea of a functional unit, and that's part of this first step in a life cycle assessment is coming up with the functional unit. Now, let's look at some other ones. And so I'm going to give you a break to talk to a neighbor. I just want you to think about these things and like, what is the function first, right? You got to know the function. What is the purpose of whatever this thing is? And then how are you going to come up with some functional unit, some basis for comparison of these two different products? So I'm going to give you just a few minutes to think about that before we talk about it together. You might not have any reference for warm garments, but it's a suitable example for my students. So if you don't know about the last one, that's okay. Fleece is a polyester. It can be made from, do you know fleece? I don't know. If you don't know the bottom one, yes, it is and sometimes it's made from, we talked about that yesterday, from mostly milk bottles can get recycled and used to make those, but it doesn't matter for the functional unit. All right, let's see what you thought about. So let's start with the middle one. That one might be easier. Gasoline versus electric powered vehicle. What is the function of a vehicle? To travel. Okay, so do you want to tell me more about this travel? So we want to cover some distance, right? Is there any other thing that you can think about between an electric vehicle and a gasoline powered vehicle that you want to make equal in order to do a fair, equal comparison? That's an output. That's not going to be the functional unit. So that is, we will need to know that, but that's not the function here. So maybe for over what time period? All right, so cover some distance, maybe for some time period, maybe it's just distance. Anything else? What do you want to put in these vehicles? Fuel? No, but I mean, remember we're talking about the function of the vehicle.
No, how much load?
Load. Okay, how much load? Absolutely. So how do you, like, this is automobiles. Let's just talk about cars. Automobiles. How would you define what kind of a load? Passengers, right? So often, so like, right, you might have a tiny gasoline powered vehicle and a really big electric vehicle. Those are not fair comparisons because you might put 8 people in the electric or your electric buses, right? Versus those are not fair comparisons. So they have to be similar sized. So we often use for transportation, we use something called a person mile or a person kilometer. Which would you prefer, miles or kilometers? Kilometers, all right. So the things like how long the engine's going to last, that becomes important when we try to actually quantify things. But the functional unit is a basis of comparison. And so the purpose is to move some number of passengers, right? And then you can compare a 6-person car to a 4-person car because you're talking about passenger miles. So that is often the functional unit. Okay. Should we do the warm garments, or is that you don't have any reference for that? No, yes, no. Okay. Wool versus fleece garment. You want to stay warm. You want to put on layers to stay warm. How are you going to make sure that they have the same function? The thickness of the cloth. Okay, so the same thickness. Is that going to Does anybody know enough about wool or fleece to know? Insulation capacity. Okay, so the thickness of the cloth works if they have the same insulating capacity, but they don't necessarily have, it's like a down coat, right? It's like it can be really thick but it versus, yeah. So the insulation capacity, right? So maybe that's associated with um, comfort at some temperature. That's the insulation capacity. All right. So it's insulation capacity. Same thing like if you're building a building, there's insulation. Even in a warm climate, you need insulation, right? To keep your air conditioning in and not escaping. It's the same thing there. You have R value is what we call it in the walls, insulation, R value, right? So if you're going to compare different insulations, you would look at the similar R value. So it's the same sort of thing there. So that insulation. All right, spray paint, roller, or brush paint for painting a house. What's going to be the function of this? So the area, absolutely. There's one more component. The area is important. Time, yeah. So for how long, right? So it might be per meters squared year or 10 years or something. It's going to be some basis of comparable, like spray painting, you might have to repaint your house every 3 years. A roller or a brush, depending upon the material, it might be every 5 years, right? So you can't compare one just meters squared because you might have to reapply more often. So these are sorts of things. And what's important about the functional unit is this becomes, it's the denominator of all quantitative So when we talked about emissions, right? Emission, that's the numerator. So for example, a gasoline power, you might have something like kilograms of CO2 emissions per person kilometer. Right? So that's what you want. And then you can compare the electric vehicle to the gasoline powered vehicle. So we need something, but what's most important about these is you have to think about what is the function and then make sure that the functions are the same, right? And so a 0.3 liter cup, they're both the same size, but they do not provide the same function. So it's always important when you think about, especially when you're comparing two things, you think about what is that basis of comparison. So it's something very, very important to figure out. And usually you figure this is out. We're talking about the goal and scoping part of a life cycle assessment where you're trying to figure out what you're trying to do and why. All right. So that was the goal and scope. So the next step is something we call the life cycle inventory. And this is where we try to figure out all those mass and energy amounts. This is where our schematic diagram becomes important. So in the life cycle inventory, you draw this diagram that has all these boxes, all the different processes that all fit together in how it's made, how it's used, what do we do, what are the other streams that come in or go out of it associated with how we use it. And then from that, we build to put on that. How much materials do you need to flow through each of the steps? How much energy is needed? And is that electric energy or petroleum fuel? Or maybe it's renewable energy. So you've got to think about all of those things that go into it. And then we sort of connect all the dots to add up all the energy all the materials that flow through. And this is a way we have to estimate the emissions. And there are different ways to estimate the emissions. So all those inputs and outputs to that life cycle assessment go in an inventory. And all of these, as I said, these are per your functional unit. So that's the denominator. That's a lot of work to come up with all these numbers. And this is the most, by far, the most time-intensive part of a life cycle assessment, is trying to come up with all of these numbers. And there's all sorts of ways to come up with the numbers, but that's the goal of the inventory. And so sometimes you have very, very long lists of all these chemicals and materials that go in and out, emissions to water, emissions to air, solid waste. All of that is part of what comes out of the life cycle inventory. So, and we often use software to help us with that, which we'll get to next week, yes. And then the last step is the impact assessment. And let me go back up this. So here we might have things like, I'm not going to write all the units, but something like gasoline. So you've got inputs, and you've got outputs. Let's say gasoline, coal, sand, cement, water. So you'd have numbers on all of these. And then the outputs might be your product. Maybe you're making cinder blocks, right? Cement cinder blocks or something of that sort. But you also have the emissions from combustion processes, carbon dioxide, carbon monoxide, NOx, SOx, particulate matter. Let's see, what else might we have here? Volatile organic compounds.
Waste.
Solid waste. Yeah, wastewater. Okay, so carbon dioxide, carbon monoxide, NOx, SOx, PM, VOCs. Please ask now if you need any explanation on what any of those are. We don't know how to quite, to totally no judgment here if you don't know. The goal is to make sure that you do know. Everybody all set on what those are? All right, so a NOx emission is not an environmental impact, right? A NOx emission goes into the atmosphere. That in itself is not the environmental impact. So the inventory tells us what the emissions are, but not what they do in the environment. And so that's what this environmental impact assessment does. It transforms what we know about what the emissions are to what the actual impacts are. And so these impacts, so these are impact categories. And you mentioned these yesterday, and there's different lists, but this is a good basis of a list. These are the environmental impact categories. And so some contribute to some impacts. Some emissions contribute to lots of impact. So if I take NOx, for example, nitrogen oxides, it might be NO or NO2. Does anybody know what impacts they contribute to? Okay, so acidification, it's not even on here, but is. So NOx would contribute there. There are others that are not on here as well. It can contribute to eutrophication because that acid rain falls into water, it puts nitrogen into the water. Eutrophication is when a lot of plant growth, right, over nutrifying water, putting too many nutrients in water, you get too much plant life. When that dies, then it's eutrophication and your water bodies fill up with plant life and the plant life dies. So NOx can also contribute to eutrophication. A couple of steps removed, but it contributes to eutrophication. So the impact assessment gathers all those different emissions and resource uses, and they put them into a fewer categories. You might have 300 inventory outputs and then 10 or a dozen impact categories. It's much easier to look at 10 or a dozen impact categories than 300, like, aluminum and copper. Like, what do I do with all that information? There's no basis for comparison. So the impact assessment is when we sort of change that into some understanding of actual impact. Sometimes a life cycle assessment might bring it to actually what we call a DALY, a DALY, which is a daily adjusted life sort of expectancy, a change in your life like deaths. Most life cycle assessments don't go that far, but it's the potential for acid rain or the potential for eutrophication. But it's a number that has more meaning for us than just NOx. NOx alone is a number, emissions is less meaningful for us. So that's the impact assessment. And we will talk about that in more detail next Monday. This NOx also contributes. Somehow somebody typed that in. That was not my typing. I don't know where that came from. Anyhow, we will leave it there. So what's the value of a life cycle assessment? The benefits, it's very broad, right? We're not looking at a narrow perspective that's going to result in unintended consequences. Especially the more stages we look at, the better our assessment and the more impacts. A lot of times, like we talk a carbon footprint analysis, that's just one life cycle impact, right? Or a water footprint, that's just one life cycle impact. A more complete life cycle assessment looks at all those impacts and tries to compare them to each other to get the big picture. Because you might be, if we talked about the CFCs, we reduced the ozone layer, but we created a greenhouse gas emission or a climate change problem. So if you did a life cycle assessment back in 1985, when they did the Montreal Protocol, we might have seen that, although we probably had no idea what the global warming potential was of HFCs at that time. Right? We didn't know enough about our chemicals, but that is the more different impact categories you have, the broader your understanding of what the challenges might be. So it's important to not do the narrow assessments, right? That's our goal, is to look at the whole system that includes multiple impact categories and multiple life cycle stages. It gets harder and harder to do that, right? The broader it gets, it's more time. You can't do it. So we're not going to just focus on isolated issues, but just focusing on like carbon footprint analysis is better than doing nothing, right? But it could be better if you're also looking at other issues. But it's not a perfect tool. So limited and accurate representative data for our systems, right? We talked about making assumptions. There are a lot of assumptions. Hopefully they're informed, well-informed assumptions, but they're still assumptions. So we've got these challenges with assumptions or lack of data. You might need to find information from a material that's sort of the same, but not quite, but that's better than no data. So there are a lot of limitations in the data. Life cycle assessments really are challenged by social impacts. At least the quantitative life cycle assessments do not get to social implications of these systems that we want. So you need additional tools, or you need some qualitative aspects to go with it. But the life cycle assessment itself does not get us there. So we have to remember it's not a perfect tool. And it can also be biased. So I just have one more example to show you a bias here, potential bias. And often life cycle assessments are done by the product manufacturer, right? What does the product manufacturer want to show? Their product's great, right? So either they compare it to something that's not comparable, or they leave out those impact categories where it's not so good. And so we've got to be careful when looking at life cycle assessments that come from product manufacturers. When they come from, like they're in the academic research or government research and some peer-reviewed journal, then that often is, at least it's peer-reviewed, right? Somebody's trying to catch some of those biases. Okay, so I'm just going to skip that. All right, so here's an example of one of the ways that results can be presented for the end of a life cycle assessment. This resource has some really good general information. It's not going to be detailed. So here's a t-shirt. It's got some weight, 100% cotton, 4 to 5 years, like 30 to 100 wearing before it's disposed of and it gets washed, right? So you have some washing machine, maybe some drying. It doesn't say how it's dried. So the per day it's worn is the functional unit in this case. And so this case, it's broken down by life cycle stage. And you can see that most of the impacts, and this is an example of results where they put all the impacts together into one numerical value. And we won't get to that for a while, but at least it's a way to compare where the problems are. So the biggest problem is in the materials and manufacturing, right? Growing cotton, this use a lot of herbicides and pesticides, they use a lot of water, it's a lot of land. So materials manufacturing is small, very little packaging, very little transport. Usage is also bigger, depending upon how you wash it and dry it, would certainly have an impact. So there's some wear, and then end of life. And so the value of this, and I just wanted to show you this up front, is by knowing that you can prioritize what you might want to change. So, and that's what's over on the right. So because the materials in manufacturing, you might choose a more sustainable material. What might be more sustainable than 100% cotton? Hemp. All right, hemp. Anything else? Organic cotton, organically grown cotton doesn't have the herbicides and pesticides on it. Might be a lot more expensive, but it will have less environmental impact. But there are different ways that you can make it, different material. And then usage, right? You could wash it less often. You could have a washing machine that uses less water and less energy. You could dry it on a line instead of a tumble dryer. These are the sorts of things that by the end of next week, we're going to be doing this by the end of next week. So we are going to be exploring in the meantime some of the lifetime impacts of different products and processes, so that by the end of it's very superficially in the time that we have, but at least to some extent thinking about how do we get through this whole process, using the tool to make decisions and prioritizing decisions. And even just knowing this information can help us think about, well, we're not going to worry about transportation. We're not going to worry about packaging or end of life. But we do need to think about how we use it, which is mostly washing, and how we manufacture. Now, this is like a very putting everything together in here. What this graph doesn't tell us is, well, what is it about the manufacturing and the materials acquisition that is the cause of this high life cycle score? Is it those herbicides and pesticides that are toxic? Is it the amount of water and land that's using? This does not tell us that. So you have to dive a little deeper. And ideally, you have a lot more detailed information than this. But this can give you the big picture about, that's where I want to at least start diving in and learning more. So this is where we're going. All right, but we can have greenwashing. So do you recognize containers like this? You have food containers, okay. And even chip bags, things like that. And I heard this, it's called flexible plastic packaging. It often has several layers all built in together to give it both the food preservation and the flexibility and the structural, the durability that you need in a food container. And there's a lot of pluses to them, but there's also a lot of challenges with them. And so my question is, can a life cycle assessment be abused? And there's a whole bunch of citations there that you'll get when you get this slide, but we're not going to go through those. But the flexible plastic packaging people did some life cycle assessments. So just what do you know about this? If you, advantages, disadvantages, just in general, any ideas? Compared to other packaging that you might have? Speak up, Indu. So it's not recyclable. Can't be reused. Any benefits? It's convenient. So I heard other people talk, but I didn't catch the words. Low cost, okay, or affordable. Yep. Anyone out? But weighs less, absolutely. So that's less material, lower transport.
Shelf life of the product. Right.
Say that again?
Increases the shelf life of the product itself.
It increases the what of the shelf life, absolutely. So you have less wasted food. Wasted food is a huge problem. All right, so you've got some sense, right? There are pros and cons to this. So if you do a life cycle assessment, then we look at, in this case, they are looking at mostly rigid containers, rigid plastics, right? Rigid plastics versus the equivalent flexible packaging. In every single case that they present the positives, right? So for laundry detergent containers, there's less carbon impact to the flexible packaging compared to a rigid PET, less material to a landfill, less material in, less to a landfill, less water use compared to steel, which is really high water use. So less fossil fuel use, and in part because the weight of the product to the, you know, the relative weight is really small, which is really a benefit. So they've got all these pluses. What did they not show? What's not on here? End of life. So there's no waste to landfill.
How much duration is this?
Okay, so that is, so it can be used like reused or just, what? Single use, right? Truly single use, right? Not you can reuse it in your kitchen. Like a sour cream container that is hard, right? You can put your leftovers in it, you can reuse it. Durability, so, but it will hold the food, either of them, I would assume, would hold the food longer. So food waste, that might be a plus, right? So in this particular case, they show all these great benefits, but they don't really talk about the challenges. And the biggest challenges is the end of life. They don't talk about the benefits of, you know, lower material weight, therefore lower transportation costs or things of that sort. But they pack tightly, and so more in a container. So anyhow, this is a biased assumption. And maybe they still come out good. But this particular case, they are only showing the positives and not any of the negatives. All right, so you got to watch out for these. They are challenging, but okay. So I'm going to summarize, and then we are going to get to work on a project. Okay, so hopefully you've got some sense of life cycle systems. It's understanding everything across the life cycle, all impacts. You really have to know what you're talking about to do this well. And a lot of people just do a life cycle assessment and they don't know what they're doing, and they come up with garbage and they don't know it. So you got to be careful about it. So it really is to identify potential environmental impacts. And the most important thing, it is our tool to make better decisions, right? That's what all of this is about. If we want to be more sustainable, we have to have the tools to assess, is it really better? So we are going to get into groups and do some drawings. I want you to think about drawing a schematic. We're going to do a plastic water bottle. Yesterday, we started thinking about plastic water bottles, so we'll do more. So Bindu, what do you want to do about groups? How many? 4 in a group. Now, these tables are a little small, I think, for the paper that we have, but 2 groups could be up here. So I don't know if you guys just want to, should we get them in group? All right, I'll do this. Okay, I see you going with those 3. Then there's 4 back there. And then we've got, let's see, 4 here. If you go back with those guys, you're 4. And then you 3 there's a group of 3, or maybe we'd have 2 groups of 3. Do we need 2 groups of 3? I might not be perfect here. So 4, 4, 4, then there's 3. So one of you guys can go back with that group of 3. And then we've got 4 here. You can go back, and we've got 2 odd people out. So maybe we can do 2 groups of 3. So figure out 2 groups of 3. So maybe 1 group of 3. You guys can be a group of 3. Okay. So we have paper. Can I introduce this first? And then 11 o'clock, yeah. So we've got enough time to get started, and then we'll take a break. I just thought I'd introduce it, and then you can take your break. All right, so we've got paper. And sometimes when doing these schematic drawings, it's you don't know where you're going. So we're going to write on Post-it or sticky notes, and then you can move those around, right? If you just start writing with markers, oops, you should have been over there. So you've got paper, we've got sticky notes, and we've got markers for you to use. We're going to do this water bottle. There is in your shared folder, is today's folder shared for them, these next 3 slides. So I'm just going to show you a little bit. So we're going to start with something like I did for the coffee cup.
Are we talking about this presentation?
No, I took 4 slides out of this one and the next 3, and we put it in the shared folder for day 2. So is the day 2 folder shared with them yet? Yeah, you can see it. All right. So you've got 4 slides here. So there's a couple of links there. So start with something like the coffee cup, but keep going, like including the people and how people use this and why people use that, because they are part of the system. So just a couple of, so this is made out of PET plastics. I don't know how much you know about plastics. Number 1 plastic, it is the most recycled plastic of any. Water bottles we recycle better than most cases. But this is sort of a general big picture of what steps are involved. This is more detail on how it is made, but I think you just really need to, you don't need all these boxes in your drawing, but you need to know that it comes from natural gas and crude oil. We make 2 intermediate products, terephthalate acid and ethylene glycol. And those go in to make our, so this would be our polymer. Then the polymer is made into what we call these nurdles. Well, nurdles get shipped someplace to make your bottles. And so that's just what that is. Bottle fabrication is generally in a mold. You know some of the other steps. And if you don't know, on the first page, there are some links. Oops. I don't know if you're going to, most of this information I've included in these other pages. And there's a lot of word details there too. So this is something that you might spend, you know, like 2 days compiling all this and learning this. I'm just going to say, here it is. And so you might want to just read through this first and then think about how you're doing this and figure out how you're going to work with 4 people at a table, but 2 teams can come up here if you want to stand.
Okay, if they fold the sheet and
You can fold the sheet if you want, but you might need all of it, at least to get started, you can. And so I'd say let's, in the next 10 minutes, before we go on our coffee break, why don't you read all the materials that you have access to in the shared drive? Just think about it and maybe come up with a plan. And then after coffee break, you come back and you actually do it. All right. And then your coffee break will be, you know, maybe an opportunity to do that too. So yeah, if a couple teams want to, these tables are a little bit wider. Any questions? All right. And I will tell you, when I come around and talk to you, I'm going to say, but how is this made? And then you're going to have to think about, oops, there's more, right? So there's always more. So I will keep you busy for an hour and a half. You might not all get to the same endpoint, but don't think you're going to end early because there's always more that you can do. All right. Okay, it's okay to not be done. These are not getting graded. What did you learn about doing this?
understand the process.
You need to understand the process. And for a starting point, what level of detail do you need to understand the process? At the start. You need to know the raw materials, okay? I would say this is the start. These big boxes are what sort of the start is. And then you can start to fill in these, right? And so I also think it's important to sort of start thinking about the big picture. And I could tell walking around the room who was an environmental engineer or who knew something about recycling, because you went into great depth about a few things. So you don't have to do that at the start. So this is sort of the big picture start. And I was sort of expecting a little more detail for what goes into that first circle, the PET producing resin, right? That you need to know it comes from natural gas and crude oil, and you've got some refining, you've got some intermediate chemicals. They get polymerized, they made into nurdles, those go into the bottle manufacture. So there are spaces for some detail. What did most of you miss on the first go around? User and water, right? So a lot of you didn't think about, there's 2 components in a water bottle. There's the water, so you've got that whole stream. And this just has, water treatment and bottling, but there's a lot to water treatment. And then user. So I was challenging, what do you need to think about the user that might impact that consumer use? Okay, so what are they going to do with it? And what might be the characteristic of a user? They might repurpose it either to refill it, or you cut off the top and you've got a little something for your house plant, right? So there's all sorts of ways to repurpose it. So the consumer has decisions to make. They might decide to refrigerate their water bottle, right? And so you might have extra energy there. Or at the retail store, right? There is also a retail store in there as part of that. They might decide to refrigerate it. It may or may not, but that is something that you have to think about. And people use it in different ways, right? Is it the everyday user who always just drinks water, or is this just a special use because you're going on a road trip and you don't know if you're going to be able to find clean water to refill your reusable water bottle? So there's all sorts of things to think about the user that may affect in the end. Remember, we want to do this so we start to think about alternatives. And I know many of you had all sorts of alternatives for end of life. We're going to talk about that in detail in a couple of days. So we've got the end of life options, lots of pros and cons to all those different options. We'll get into more details on that. But the user is, not a homogeneous one size fits all, right? And there's different decisions that need to be made. So remember, we're doing this because we want to get to the point where we can make decisions about doing better. And understanding the why we have these to begin with and how they're used is an important part of the whole system, right? We might be able to tweak and fix the end. Do we send it to chemical recycling or mechanical recycling? We can fix that, right? We can make that better, but we still might have lots of plastic water bottles. So we're still making lots of plastic water bottles. So there's all sorts of things to think about. And what I think in this first step, we're just challenging you to think about the big picture. Maybe you don't put that all in a life cycle assessment, but that's the first, is that understand your system, the whole system. So do you think that you know more about plastic water bottles now and how they're used and how they're made than an hour and a half ago? Okay, so it doesn't take long to get that first step, right? And this was an example that you know something about, right? You've used them, you have some idea of where you put them. You put them in the recycle bin or the trash bin. So you have some relevance and some familiarity with this particular product that you might not have, or like in your research. Hopefully some of you who talked about life cycle assessment and research, you should know about your system and how it's used in whatever you're doing. You should know a lot about your product. Okay, so just a couple of details. I said processes and boxes, flows. I had to remind some of you of this. That's just a standard approach, right? So each box is like what I would call a unit operation. And it could be like a clump of unit operations. So I think that team back there did a good job of just having the clumps of unit operations. We didn't need every single individual refining step, or water treatment might take several steps. For now, starting to putting water treatment into one box. You've got chemicals and energy coming in, and you've got surface water or groundwater coming in and drinking water coming out. That's okay at the first level. But then you've got to know that every one of those sort of big boxes has a whole detail, and we're going to talk about that later, detail of like the refining process or not. But so by just standardization, the processes go in box and then the materials flow between boxes. All right, anything else that you learned? So I didn't at this point ask for like emissions out. Some of you did do that. We'll get to that level of detail next week. But mostly we were trying to get to like this plus more detail than this, but sort of something along that line. All right, so this afternoon, we are going to be in a different location. And I don't see, I don't see, are any of the TAs here? It's like everybody left other than me. We're going to be in a different location that Bindu has sent you, I think in the WhatsApp, you know where to go. So it's almost 12:30. We just have a few minutes left. So I was going to do another half hour of lecture right now, but I decided to let you have more time because you are all being very productive. So being productive is the most important thing of our time together. So I gave you more time to do it. So after lunch, we'll have a little bit more discussion about life cycle inventory. And then we are going to break you into teams, the team that you are going to be together with on your project part, which we're going to pick away with little pieces before next Friday. You will have done this. So this afternoon, we're going to do this again. So you're going to be with different people. So Indu is breaking you into teams just to mix a range of like undergraduate students with faculty and environmental engineers and non-environmental engineers and non-engineers. We'll mix you up so that the teams will have different groups of expertise. And we will tell you, it looks like you've got your teams here. We will tell you those this afternoon. I'm just giving them the heads up. So we will break you into teams this afternoon. And then we have a whole bunch of products that we have some life cycle assessment details for. But this afternoon, we're going to get started on the same thing. This was your practice. That's why I said it doesn't matter if you're not done and you don't think this is perfect. This was practice. This afternoon, you're going to get started on doing the same thing for whatever product your team picks. So we've got, I don't know, 8 or 9 different product ideas for which we have some data for. So that's why we're not letting you just go do anything, because getting the data takes, that's the months, right? You don't have months. So we're only giving you options for which we will feed you more data over the time. But this afternoon, we're going to draw this again, but not for a plastic water bottle. So do you have any more general questions on how to do this? What goes into this? How to think about this life cycle thinking and the whole system thinking, including the user and all the component parts. And we didn't get to equipment, but there's equipment and all of this. So do you have any questions about this kind of drawing? There's always a chance of missing some aspects. And that's part of the reason why we use Post-its, that a couple days later, a couple days from now, you say, oh, I didn't know that, or I know more now, so I'm going to go and add that. So these are not this afternoon once and done, and then you're stuck with it. It is a start. And that is true for all life cycle assessments. You might think you are done, and it's like, I forgot something. Or I just learned something, right? This is a forever learning, always learning and making it better. So yes, it's very possible you might have missed something, but there will be opportunities to rectify that situation. And oftentimes life cycle assessments aren't perfect, right? They haven't captured everything. The goal is to capture the big stuff. And so I would start with thinking this afternoon, the big things first, right? And then dive into the details. So you can start with the, sorry, I got lots of clicks here. Start at this level, right? And maybe there's a big box on for this level of detail for whatever your product is going to be. And then either on different paper or within the little box, or somehow start to fill in the details, but you got to understand the big picture. And I want you to think about the other aspects too, especially like the user, because user behavior is a big impact of the environmental impacts, or a big cause of the environmental impacts. New academic complex 2. Okay, and is that close by? Okay, so you'll give us a map before the end of lunch. Okay, I'm not going to give you all this, right? So some of them have more or less information like this. You might have to go find. So some of the afternoon might just be learning, but the goal is to at least start drawing the big boxes that you will know you'll have to start to fill in. All right?